Oh, hey guys. Hey, I'm just putting together sets of pencils, colored pencils, a red one, a blue one, a yellow one, and a green one, all in the same set. And I'm trying to make as many sets as I possibly can. But it looks like I'm going to run into an issue, and that is that this is my last red pencil. Yeah, I've still got the other colors left over, but I'm out of reds, and therefore I can't put any more sets together after this last one. This is a lot like a concept that we're going to be talking about in this video, the concept of a limiting reactant. Just like I ran out of red pencils when I was making my sets, in the same way in a chemical reaction, we may have one reactant that we run out of first, and then we have excess of the others. In fact, that's the way it normally happens. So my red pencils would be an example of a limiting reactant in this case, whereas blue, yellow, and green would be examples of excess reactants. Let's take a closer look at limiting reactants and how they work in stoichiometric problems. Here we go. It rarely happens that we're going to have a reaction in which we have perfect ratios of the reactants involved. In other words, completely balanced, everything's absolutely used up. It just doesn't really occur that often. More often than not, we're going to have a reactant that's completely used up and another reactant that's in excess. There's some left over. And the amount of product that's actually formed in that reaction depends upon that reactant that's completely used up. We call that reactant the limiting reactant. And as the name suggests, it limits the extent of the reaction and determines the amount of product that's going to be formed in that reaction. All of the other reactants are going to be left over after the limiting reactant's been used up. We call those excess reactants. We're not always going to be told which reactant is limiting and which reactant is in excess. So how do we figure that out? Let's use this reaction as an example. The reaction between phosphorus and oxygen to make tetraphosphorus dicoxide. Let's say that we're given a problem in which we have 25 grams of phosphorus, 50 grams of oxygen. And they want to know how much product we can make from those conditions. Again, we don't know which one is which one is limiting and which one's in excess. So let's use our steps involved in solving a stoichiometric problem and do one set of steps for phosphorus and one set of steps for oxygen. The one that allows us to produce the least amount of product is our limiting reactant. And furthermore, the product that we make from that limiting reactant is all we can do for this reaction. So I'm going to do this two different ways. One with our stoichiometric steps, and then the second way I'll use the magic number method. First things first, we must balance our equation. So when I look at this equation, I can see that I need to balance the oxygen. So I'll put a 5 in front of the oxygen, and that will balance my equation. Let's first calculate the amount of product that we can form from 25 grams of phosphorus. We start with our phosphorus, and the next step is to find the number of moles of phosphorus by dividing by the molar mass. 1 mole of phosphorus, 1 mole of P4 has a mass of 123.9 grams. By the way, I took that number from the periodic table. Our next step is to use the mole ratio between the substance we have and the substance we desire. In this case, it's a 1-to-1 ratio. But for the sake of practice, I'm going to go ahead and put that in place. So 1 mole of P4O10 for every 1 mole of P4. Now, using the moles of my product, I'll calculate the mass by multiplying by the molar mass. So the molar mass of P4O10 is 283.9 grams. In arranging it this way, I can cancel my units, and now I just perform the math. 25 times 283.9 divided by 123.9. That gives us a product mass of 57.3 grams. Let's check now with the oxygen. I start with my 50 grams of oxygen, and now I'm going to convert to moles by dividing by the molar mass. 1 mole of oxygen gas has a mass of 32 grams. Next, I'll convert to moles of product by using the mole ratio between oxygen and tetraphosphorus dicoxide. As you can see, it's a 5-to-1 relationship. But I want to write it this way, 1 for every 5, because I need 1 mole of P4O10 for every 5 moles of oxygen. I arrange it this way, of course, because I don't want moles of oxygen anymore. I want those to cancel. I want to be left with moles of P4O10. And finally, I'll use the molar mass to convert from moles to grams. Just as before, I have everything properly arranged, and now my units cancel. I'm left with grams of P4O10. 50 grams times 283.9 divided by 32 divided by 5 gives me 88.7 grams. And now I have no trouble determining the limiting reactant. It's the one that produces the least amount of product. That means phosphorus is my limiting reactant. And it means that the most product I can make is 57.3 grams. Let me show you now how we can determine how much excess oxygen we have. Let's start by determining how many moles of each of these reactants we actually have. 25 grams of phosphorus divided by the molar mass gives us 0.202. 50 grams of oxygen divided by its molar mass gives us 1.56 moles. Now remember, we only need a 5-to-1 ratio between oxygen and phosphorus. That means we should have 5 times the amount of moles of phosphorus. 5 times 0.202 means that all we actually need is 1.01 moles of oxygen. That means we have an excess of 0.55 moles of oxygen. When we take that 0.55 moles of excess oxygen, multiply it by its molar mass, we get a value of 17.6 grams of excess oxygen. Once again, when we have this reaction, 25 grams of phosphorus, 50 grams of oxygen, we have a maximum yield of 57.3 grams of tetraphosphorus dicoxide. And when that reaction is complete, we're going to have 17.6 grams of leftover oxygen. Okay, let's solve this problem one more time, but this time let's use the magic number method. First, I have my balanced equation on the board. This is step 1. Always start with a balanced equation. Next, I'm going to place an X and the molar mass in front of each substance. Now that I have all my molar masses and my X's in place, I'm going to multiply all the items together in front of each one of the substances. 123.9 times X gives me 123.9X. 32 times X times 5, yes, I include the coefficient, that gives me 160X. Finally, 283.9 times X gives me 283.9X. Next, I'm going to set each of these expressions equal to the masses I've been given of those substances. I was given 25 grams of P4 and 50 grams of O2. Now I solve for X. As you can see, I have two values of X. X equals 0.202 and X equals 0.313. Now here's the key. The smallest X value belongs to the limiting reactant. Let me say that again. The smallest of these X values is going to belong to the limiting reactant. So which one is the smallest? Obviously this one, 0.202. And sure enough, it belongs to P4. We already established last time that P4 is indeed the limiting reactant in this situation. To find my product, all I have to do now is take this value of X and plug it in for X here. 283.9 times 0.202 gives us a value of 57.3 grams of P4O10. And look at that, the same thing we found the first time. What about the excess oxygen? How do we solve for that? It's actually pretty simple. We take the difference between the two X values. Taking the difference of the X's, we get a value of 0.111. All we have to do with this difference is plug it into the expression that belongs to our excess reactant. So 160 times 0.111 gives us a value of 17.6 grams of excess oxygen. And look at that, just like we determined in our last example. Let's talk about one last concept with stoichiometry, the concept of percent yield. In our problem, we determined that 57.3 grams could be produced from these conditions and this reaction. Emphasis on could be produced. So this number we calculated would be our theoretical yield. It's the maximum amount of product that can be possibly produced from these given amounts of reactants. But rarely does it happen that we'll actually produce the theoretical yield in a reaction. Let's say that when we were given that problem, we were also told that in the course of real-life activity, when the reaction is carried out in experimental form in the real world, we get an actual yield. And let's say for this example that we had an actual yield of 52.0 grams. This is something you'd be given in the problem. We can calculate how efficient our reaction was by calculating the percent yield. Percent yield is simply the ratio of the actual yield to the theoretical yield, and we express it as a percent. So we multiply it by 100. So again, to find the percent yield, we take the actual yield, divide it by the theoretical yield, and multiply it by 100. In our case, we were given an actual yield of 52. We had a theoretical yield, one that we calculated, of 57.3. We multiplied by 100, and we get a value of 90.8%. That means that our real-life reaction was 90.8% efficient. Not bad. So laboratory chemists work hard every single day to try to limit the amount of error that goes into a reaction so that they can get this number as high as possible. Here's your homework problem. Let's say you have this reaction. The reaction of nitrogen with hydrogen to produce ammonia. I've already balanced the equation for you, and I've given you amounts of these reactants. We have 50 grams of nitrogen and 25 grams of hydrogen. Based on those conditions, tell me how many grams of ammonia you could theoretically produce. Also tell me which one of these is the limiting reactant. You can put your answers in the LMS. That's all the time we have for this video. Today we talked about limiting reactants and how we can go about calculating the limiting reactant in a stoichiometry problem. We use two different ways of doing this, our stoichiometry steps and the magic number method. We also talked about how to find the excess in a reaction, and we talked about how to find the percent yield. And there you go again, finishing another chapter. That's the end of chapter 11. In our next chapter, we'll talk about different states of matter. I hope this has been helpful to you and beneficial, but let me know if I can assist you in any other way. Until next time, God bless.